Okay, so consider the rate of reaction versus time graph showing the Hepa process of equilibrium if the volume of the reaction is a reaction vessel is doubled at T1, should have a rates of forward and reverse rates of reaction change over time. Okay, so as I always, you've got to think about it: forward rate of reaction, reverse rate of reaction, work out what's going on. So the volume is doubled, which leads to a pressure decrease. What happens to the forward rate of reaction? That's decreased. What happens to the reverse rate of reaction? That's decreased. So this is the Hepa process, and this doesn't have the equation on, so here is the equation. Okay, when you're dealing with pressure changes, you need to think about how many gas particles there are on either side, and since all of these are gas particles, there are 4 on this side and 2 on that side. If there are 4 and 2 on that side, remember that the reaction that produces, that makes less particles is more affected. If it's more affected, the reaction that makes less particles, that's the forward reaction. Since both the forward and reverse rate of reactions go down, the forward is favored. And that's what we need to know for that. Okay, so let's go draw this out. So the forward has to go down. So forward goes down. Okay, let's just say that it ends there. Right, the reverse goes down. Okay, so they both have to go down. That's what you have to show. Then they have to re-establish equilibrium at T2. And they should re-establish equilibrium between the two. So effectively halfway in between. So halfway in between, there's 3 squares. So halfway in between would be 1.5 squares, which would be here. That's where you want to end it. Remember, you should always draw where you want to end stuff before you start drawing the curve. And so there we go there. And here we go here. Oops. All right. And remember, effectively, we should try and not have these lines touch until the thing, right? And that would be there. And then, oops, sorry, that's not right, because that T2 there is actually here. So they should be able to touch there. Okay. And then they should continue on there, and you would use a ruler, but Mr. Lim's lazy. Right, there. Let's go through this next bit. Okay, complete the table below to predict the effect of the following imposed changes on the system when initially at equilibrium. Okay, so let's go grab the equation. Yep, and let's move that down here. Where'd it go? Here it is. Okay, cool. Let's just leave that there. Okay, so I'm going to increase the temperature, and hopefully you guys know that this is a delta H equals a negative value, negative 92 kilojoules. Okay, so please remember that there are 2 different ways to show endothermic reactions, one as a reactant or product, or one as a delta H positive or negative, and be able to read both of those. Increasing the temperature will have what effect on the rate of forward reaction rate after equilibrium has been re-established, so that's even further wrong. Okay, so increasing the temperature, that will increase, right? That will increase no matter what. Removal of some ammonia. So remember when we do this forward rate of reaction, reverse rate of reaction, then which one is favored? Okay, so forward rate of reaction here, if I remove some ammonia, unaffected. Reverse rate of reaction goes down. That means the reverse is favored. But you should remember that that's the initial change, right? The final change is dependent on what happens to those rates of reaction over time. And so this, if we were to draw the rate of reaction graph over here, okay, the forward would be unaffected, the reverse would go down, and then they would go together like that. So actually the forward has decreased compared to what it was before. So the removal of some ammonia is a decrease. Okay, increasing the partial pressure of nitrogen, that increases the forward rate of reaction. The reverse rate of reaction stays the same. So that's an increase here because so even though the rate of reaction goes down after, right, it's actually going to be higher than what it was before. So the forward will go up, the reverse will stay the same. And then that one will go down, that one will go up, but still the forward went up, the reverse went up. Okay, so that's increased there. Okay, next is the effect of magnitude of equilibrium constant. So the equilibrium constant is the K value. The K value is the ratio of products over reactants. Okay, that K value only changes when temperature changes. So that means that if you remove some ammonia, no change. If you increase the partial pressure of nitrogen, no change. However, with the effect of the magnitude of equilibrium constant on increasing temperature, we have to consider whether this is a endo or exothermic reaction. It happens to be an exothermic reaction forward. If it's an exothermic reaction forward, the forward rate of reaction and the reverse rate of reaction, forward rate of reaction goes up, reverse rate of reaction goes up. Which one goes up more? The endo, which happens to be the reverse. If the reverse goes up more, then the reverse is favored. If the reverse is favored, the reactants go up, the products go down. If the reactants go up and the products go down, the K value will decrease. Okay, next. All right, this one here. On another occasion, the system synthesis of ammonia gas from nitrogen hydrogen gas performed in a 4-liter thing, blah, 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 right, at 100 degrees. Which substance does line 1 represent? So here we have to look at line 1 and line 2 and line 3. We should recognize that these two here are linked because they both go down, and this one here is something different. Which side of the equation has two things? So these must be the reactants, and this must be the product. Happy with that? So that means that this one is the NH3. Then we look at the line 1 and 2, which one's the N2, which one's the H2. Other information shown on a concentration time graph is the stoichiometry change of the two things. So this one changed from 0.8 to 0.5, which is a change in 0.3. This one changed from 0.4 to 0.3, which is a 0.1 change. So the change in the line 2 was only a 1 compared to a 3 or 3 times as much for line 1 compared to line 2. So which one has a 3 coefficient? It's the H2. So the H2 is there, and this must be the N2. Okay, why? So it is the H2. Why? The change was 3 times line 2, and 3/2 of line 3, right? So effectively it had the correct stoichiometric ratio. At what time was equilibrium established? I think it was time 5. Don't forget the minutes. How many moles of the substance are represented by line 1 are in the flask at equilibrium? Okay, so at equilibrium it's over here. Okay, at equilibrium over here, it's 0.5 mole per liter, right? That 0.5 mole per liter is its concentration. But we also know its volume. It's in a 4-liter flask. If we know that it's in a 4-liter flask, therefore the volume is equal to 4, and so therefore the number of moles is equal to 2. All right, next one. So this one here asks you for the same reaction as the last one. Draw on the graph below, show how the concentrations of each substance would change over time if the reaction was carried out at a temperature of 300 instead of 100. Couple of considerations. Because it's at 300 and rather than 100, equilibrium is going to be established faster. Not only that, you have to also consider changes to yield, because maybe the amount of stuff will have changed, right? So if the equilibrium is established faster, we have to make sure that our endpoint is somewhere before time 5. Then if we increase the temperature for this reaction, remember it's N2 plus H2 goes to NH3, 2 here, 3 here, it's a delta H is equal to -92, so it's an exothermic forward. If it's an exothermic forward, so this is an exothermic forward, If that happens, then the a temperature increase results in an endo being favored, which happens to be the reverse, which means that you're going to have more reactants and less products. Okay, so if you have more reactants and less products, that means you're going to have this line here has to go up, this line here has to go down, up, and this one has to go down. Okay, remember that you also have to take into account stoichiometry. Right, so therefore then you have to think about it. Okay, this one starts at 0.8. What value can I change it by? I would just change it by the squares, and I would just say, okay, at 3 minutes, because that's a time before 5, that's when it's going to finish, so it's going to be 3 squares there. Okay, this one starts at 0.4. If that one changes by 3 squares, this one will change by 1 square. And if this one starts at 0, this will change by 2 squares. Okay, which means that those are my 3 things I need to draw. I would zoom in an exam, yes, so get nice and close and try and draw that as best as possible. Right, that was not great. And then I would erase it and then do it again. Okay, and this one here. And then I would get a ruler to finish off that one on the line, if I had a ruler. All right, so on and so forth. Okay, so then next, in the manufacture of ammonia, there are 3 key reactions, blah, blah, blah. With the aim of increasing the yield, the factory operator must decide to use a low temperature and a high pressure. Which reaction would most benefit these conditions in terms of increasing the yield? So we have to think, right? Low temperature means that we are picking an exothermic, because low temperatures favor exothermic reactions. So that means that one is out of the question, right? So then out of those 2, which one would benefit from a high pressure? A high pressure means that you're favoring the reaction that makes less particles. Which one makes less particles? Well, this one here makes 2 and 2, which means they're equal, so that's not affected. This one makes 4 and 2, which means that a high pressure will be affected, so therefore it's this one here. Okay. All right, next. The manufacture of ammonia on industrial scale carried out the Hepa process. Hey, we knew that. Blah, 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 blah. In the space below, draw a fully labeled enthalpy level diagram for the Hepa process showing delta H, EA, catalyzed and uncatalyzed reaction pathways and axes with the correct units stated. All right, so enthalpy diagram, axis, interesting. Right, so this one here, remember enthalpy diagram should be progress of reaction and not time. Why shouldn't it be time? Because these things change almost instantaneously, and so therefore you can't really show that correctly then if you were to draw this with time. And then this one should be H, or enthalpy. And this would be kilojoules per mole. All right. Then you would draw, right, it's an exothermic reaction, so you should draw an exothermic reaction. Right. So we know that this is your delta H. More importantly, we actually also know that it is equal to 92 kilojoules. So we could probably draw that out as well. Okay. The EA is this one here, from your transition state to your reactants. So this is, whoops, that's not a triangle, that's EA. Someone asked if we needed to draw the reverse activation energy. You do not. Right, but make sure that you draw that one right down to there, and you draw like a little dots to show that, yeah, I understand where that's supposed to end up. Okay. And then you need to draw a uncatalyzed and catalyzed reaction. So we should label this one as the uncatalyzed. And then we should draw a catalyzed reaction here. Right. Ah, interesting. Actually, no, that's fine. Yep. Okay, cool. So then that's the catalyzed. We probably also need to draw an EA, catalyzed and uncatalyzed. Okay. That'd be easier to draw on a bigger piece of paper, but yes. Right, so those are probably all the things that you need for that one there. Right. Okay, next. Sealed vessel, equilibrium mixture of the Hepa process stuff. At time 1, the temperature of the vessel was increased. So T increase. Okay, so if the temperature increased, again, here's the equation. NH3 2 delta H equals negative 92 kilojoules. Okay, so it's exo forward. If it's exo forward, that means that the temperature increase leads to endo favored. Endo favored means that's the reverse favored, which means that you have more reactants and less products. Okay, so more reactants and less products. What's going to happen? More reactants, less products. We're going to have the N2 go up and the NH3 go down. Now remember, this is a concentration time graph, so which means that you need to take into account stoichiometry as well. You don't have to do that for a rate of reaction graph. So if that is X, this has to be 2X. And I would, in an exam, I would get a ruler out and I would measure it out, right? And hopefully they would give you a grid, but that's the idea, right? So I would zoom in and I would draw this out appropriately. And this one here. Okay. You could show that if you wanted to for the examiners to be like, yeah, I understand what I'm doing, but like you don't have to, right? Then you would get a ruler and you would rule this straight. If you don't use a ruler and it's not perfectly straight, then you probably will lose a mark, right? So then T2, what happens? T2, all the ammonia was removed from the system. So the NH3 down. So the NH3, which is this one, all of it was removed from the system, so its concentration goes down to 0. What happens to the other one? Nothing yet, not at that point in time. Okay, so what's going to happen is that the reverse rate of reaction is going to decrease to 0 and the forward rate of reaction is going to remain the same, which means that the forward rate of reaction is favored. So actually, should I write that all down? Forward rate of reaction, reverse rate of reaction goes down to 0, forward rate of reaction stays unchanged. That means that the forward is favored. If that forward is favored, that means the reactants go down and the products go up. Okay, so this one here, this one will go up, and let's just say that that one there, it goes up by that much. Remember that this is going to be 2x, which means that this one can't change by much. It can only change by, which way is going to go, up or down? Down by x, okay? So a small amount. So it means it should go to here, and I would zoom in again and draw that as best as I can. There. Okay. And then I can get rid of this stuff here whilst I'm up so close. And then this one here. Okay, and then you would draw onwards, making sure that you use a ruler and it's as horizontal as you can get. Okay, and then you can get rid of these ones because you don't need to show that. Okay, cool. All right, so that's what would happen. Okay, next. All right, Hepa process. Periodically, the ammonia is removed from the reaction chamber. What immediate effect would this have on the rate of reaction? The forward rate of reaction would increase, but you remove ammonia, the forward rate of reaction is unaffected. The reverse rate of reaction would increase, but the reverse rate of reaction would go down to 0. The forward rate of reaction would decrease, but unaffected. The reverse rate of reaction would decrease to 0. That makes sense. Right. Which of the following conditions maximize both rate formation and equilibrium yield of ammonia? Increase concentration of reactants, yes for rate, yes for yield. Increase pressure caused by a decrease in volume, yes for rate, yes for yield as well, right? Because this makes less particles. Increase in temperature, yes for rate, no for yield. Addition of catalyst, yes for rate, no for yield. Okay, so therefore it's just 1 and 2 there. Okay, so if I was to do rate and yield, this would be a yes, yes, no, and yes and no. Okay. All right, next, contact process. Ooh, yeah, here we go, something different. Okay, which of the following sets of condition would both increase rate and yield? So again, rate and yield. Okay, so increase rate, high temperature, yes. Increase yield, low pressure. Oh, yeah, we don't need this one. So this is let's zoom in. High temperature, yes, for rate. Increase yield, low pressure. Low pressure will favor the reaction that makes more particles, which is the reverse, so that's no. Right, high pressure, increase rate, yes. Low temperature, increase yield, yes, because it's exothermic. Low temperature for rate, no. High pressure for yield, yes. And low pressure for rate, no. And high temperature for yield, no. Okay, so I would go through all of them just in case something is different and then not what you're expecting, and then you have to rethink about stuff. I will always go through it and eliminate all of them. All right, so that's B. Okay, key reaction is this, blah, blah, blah. Following graph shows a reaction thing. Is the reaction endothermic or exothermic as written? Okay, so let's have a look. The SO2%, this is the percentage of SO2 converted to SO3. So that's effectively the yield of SO3. This is the temperature. As you can see, as the temperature increases, which is effectively that way, the yield decreases. Okay? As the temperature increases, the yield decreases. So the temperature increase leads to an endothermic favored. If the endothermic favored makes more, this one here, a yield decrease means that there is more reactants and less products. The reaction that makes more reactants and less products is reverse favored. And so therefore the endothermic is favored, the reverse is favored, so therefore the endo is reverse. So justify your answer. What you would do is something like along the lines of reaction is endo or exo as written, so therefore it's exo as written, 1 mark. Right, justify your answer. So you would identify that as the temperature increased, the yield decreased. So that's just identifying the information from the graph. Right, then you would go into your long ass explanation about saying, okay, the temperature increase means that there is the endo is favored. Since the yield decreased, that is a indicator that the reactants went up and the products went down. And so therefore, that's a reverse rate of reaction favored. Since that's a reverse rate of reaction favored and the endo is favored, so therefore reverse must equal endo, and therefore the forward must be equal exo. All right, that's that. Complete the following table by stating pressure conditions high or low, which would result in what? Okay, high rate or high yield for this contact process. So fastest rate would be a high temperature. Wait, what's this? Pressure. High pressure for rate, good. And remember, this is the SO2 plus O2 goes to SO3, 2, they're all gases. Okay, and then in terms of highest yield, this one makes 3 particles, this makes 2 particles, so this one, forward makes less, which means it's affected more, so you want to increase that so that it's increased more, so you want a high pressure. Okay, so fastest rate, justification, this would be the whole rate of successful collision. So increase pressure leads to increase frequency of successful collisions. Probably you want frequency of collisions, which leads to increase frequency of successful collisions, which means that the rate increases. But the highest yield, okay, so you would say that increase pressure increases both rates of reaction. reaction that makes less particles affected more. So forward makes less particles, increased more, increases rate of reaction, increases yield. Okay. When actually done, this is done at 1 to 2 atmospheres. Why? So always remember that if you have it at high and high, there's no compromise between pressure for yield and rate, but you do have to have safety and cost considerations. And effectively what that would mean is that you can get a good rate and yield at low pressure. Okay, so therefore if you can get a good rate and yield at low pressure, therefore there's no benefit to increase the pressure, because that will just come at safety and cost considerations. Right? Okay, next. Question is about production of sulfuric acid, blah, 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 blah. Oh, graph this. Yeah, I hope you'd all know how to graph. I hope you know how to graph. Describe the trends shown in these results. Oh, I don't remember what those are. Okay, so I think what it was that the yield went down as the pressure went up, temperature went up. Yeah, I think so. Yeah, so describe the trend. So as temperature increased, the yield decreased. Okay. As a result of his findings, the chemical engineer decides to operate the sulfuric acid plant at 200 degrees Celsius. However, the amount of sulfur dioxide produced was very low, right? Suggest a reason for this. Well, we've decided that 200 degrees Celsius you get a good yield, so why might there be another reason why you don't produce a lot? Because it's not as a high enough rate. So not a high enough temp to get a good rate. After further tests, it was decided to operate plant at 400 degrees Celsius. With reference to your graph, explain why this temperature, not a higher temperature, was chosen. So having a look back at that graph, at 400 degrees, you still get a yield of 92%. So 92% is still a pretty good yield. If it's still a pretty good yield, that means that you'll have a good rate at 400 as well as good yield. Okay, all right. So assuming a yield of 92%, calculate the volume of oxygen and pressure of 152 kilopascals required to produce 1 ton of sulfur trioxide. Okay, cool. So let's go do this. Okay, so you want to produce 1 ton of sulfur trioxide. Okay. However, your process to make this is only 92% efficient. Right? If this process is only 92% efficient, to make 1 million grams, you have to aim for slightly higher, because your 100% should be a value which is 1 million plus a bit. Right? So you have to work out how much that is to actually aim for to get the required 1 million grams. All right, so we are going to calculate the amount that we need from the amount that we're going to work out the blue value, the 100% from the 92%. So the mass of SO3 actual is 1 million. The mass of SO3 theoretical that we need from that is going to be the mass of the SO3 actual
times 100 over 92. Okay, the idea here is that we are going to divide it by 92 to get to 1%. Divide by 92 to get to 1%. Find out how much 1% is, and then multiply it by 100 to get to 100% of that value. Okay, and that value is, I don't know. I'm not going to go look it up because I don't have a calculator near me, but let's just say that value is A. All right, so if that value is A, right, then what we're going to then be able to do is work out the number of moles of SO3 theoretical by doing the mass over the molar mass of SO3, which will be equal to B, some value there, right? Then what we're going to do, we need to work out the volume of oxygen required to produce that much. So we need to work out the number of moles of O2, okay, which will be equal to the number of moles of SO3 theoretical times 1 on 2, because we got a 2 and a 1 there, so we get half the number of moles, which will be equal to B on 2, which will be equal to some value, so we'll call C. All right, and then we can work out the volume of that oxygen. PV is equal to nRT, so therefore nRT over P is the equation. So therefore the number of moles of oxygen is C, we times it by R, 8.314, times it by T. What temperature is it at? 400 degrees Celsius. So that's like 673.15, converting that to Kelvin at a pressure of 150 kilopascals, and that value will be something there. Okay, and so that's how you would do it. Okay, the important part to know is to recognize that, okay, well, this is the amount that we're going to actually try and get, so therefore we need to recognize that that's the 92% value. We need to get to the 100% value, which is like the 100 million and a bit. And how to get there, you times it by the 100 over the yield. Okay, next. So what have we got here? We got biodiesel. Okay, so whoops, that's not what I wanted. There we go. Right, so what is biodiesel? How can trialine be converted into biodiesel? By naming the chemical reaction and stating the additional reactant required. Okay, so what do we need to do? What is biodiesel? It is an ester of a short chain alcohol, either a methanol or an ethanol, and a long chain fatty acid, alternatively a hydrocarbon chain. Okay, so effectively it is a methyl group here attached to a ester group attached to a long carbon chain here, where this part here has to be 14 plus carbons. Okay, all right, so that's that one. Describe how trialine can be converted into biodiesel. The reaction is called trans-esterification, or just esterification, because you're effectively making an ester. Esterification, right? And what additional reactant do you need? A short chain alcohol, either a methanol or a ethanol. All right. An alternative catalyst for the production of biodiesel by this method is the enzyme lipase. State two similarities and two differences in the way that NaOH and the lipase catalyst function in the process. So two similarities. So similarities would be something like they both increase rate of reaction and that they both not consumed in reaction. Okay, two differences would be something like that NaOH can make soap, lipase will not. Alternatively, you can talk about the idea that NaOH is much more energy intensive because you need to run it at high temperatures. okay, whilst lipase runs at low temperatures. Okay, so the difference is you need to state that one does that and that one does not, something like that. Okay. All right, the next one. So let's have a look. What do we got? Biodiesel, blah, blah, blah. See there, transesterification reaction between oil and methanol. Many different types of oils, blah, blah, blah. Explain why biodiesel is considered a more suitable green alternative to traditional fuels such as petrol. So the idea that it is a renewable resource, because effectively you can grow it and then grow plants, turn that into the fuel, and then grow some more plants, compared to fossil fuels, which are non-renewable. Alternatively, it's also it's just not dug out of the ground. Okay. Any others? Yeah, probably. The idea is that effectively, if you do this right, this can be a carbon neutral thing. Like burning the biodiesel still produces carbon dioxide, but like because you're growing something and you're capturing that carbon dioxide out of the air, in theory it can be carbon neutral. There's still carbon used in the or carbon dioxide produced in the production process, but if you do that right, you can also probably minimize that as well. All right. So example of this is there's a triolene, blah, blah, blah. Okay, so complete the reaction above by showing the filling in the boxes. So you got to draw glycerol. Okay, carbon, carbon, carbon. 2 hydrogens there, one hydrogen there. And glycerol, hopefully you remember from soap production as well. You've got your thingamabobs, all your hydroxides there. And then biodiesel is a methyl ester. I think that, they're using a methanol, so it's a methyl ester. And then, as you would zoom in, you would effectively have to copy this. Oh, I know what I can do. Oh, look at this. Copy. Oh, Mr. Lim, you're so lazy. Yeah. All right, copy that. COO with a methanol group on the end. That's exactly how I roll. So when the exam, you get your scissors out, you cut that thing there and you paste it in there. That'll totally go down well. All right. Okay, next. Due to the slow rate of transesterification, you've got your catalyst and temperature things, blah, blah, blah. So how does a catalyst increase rate of reaction? So this is all the way back to year 11. So it reduces amount of energy required for a successful collision, i.e. reduces EA. What does that mean? That means that there is a greater proportion of particles, and this is all of the kind of the collision theory stuff that you need to be able to explain. Greater proportion of particles with sufficient energy and and increases frequency of successful collisions. Okay, so that would be that one. You'd have to write most of that to get the mark. Okay, then a temperature of 60. Okay, so what does a temperature of 60 do? Increases average kinetic energy of all particles, which leads to an increase proportion of particles with sufficient energy, and again increases frequency of successful collisions. Okay, so the idea that you are relating it to the kinetic energy, the sodium hydroxide catalyst reduces the amount of energy required for a successful collision, but temperature increases the kinetic energy of the particles. And thus these words here, proportion, really important, sufficient energy, frequency, always super important. All right. All right. Next, what do we got? During the manufacture of biodiesel, unrighted side reaction occurs where soap is produced. It's problematic, blah, 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 blah. Explain how the soap producing reaction can occur. So in other words, something along the lines of the NaOH reacts with fat/oil, creates soap molecule instead of the methyl ester of free fatty acid. Alternatively, that's also known as the biodiesel. Okay, so effectively you create the soap molecule instead. Okay, current research is focusing on an alternative catalyst for biodiesel manufacturers called the lipase. When lipase is used to catalyze some transesterification, this prevents the alternative soap producing pathway. Why? Enzyme. Describe what an enzyme is and explain what enzymes are able to minimize the occurrences. Okay, so this is about enzymes. So, what is an enzyme? Enzyme equals biological catalyst. Okay, so then what else? Explain why enzymes are able to minimize the occurrence. Okay, so enzymes have specific shapes and only catalyze specific reactions, and you can talk about the lock and key model or the induced fit model. Okay, so about their shapes, and they can only catalyze specific reactions, and so therefore soap reaction will not be catalyzed. And plus, when you're using a lipase, there's no sodium hydroxide, no base for soap reaction. Okay, but it's really more about the lock and key, the enzyme shape, this part here. Okay, all right, next. Let's have a look. Move, damn you. Here we go. Following statements about biodiesel is correct. Base catalysis has a higher reaction rate, unlike lipase catalysis, can cause saponification, which decreases biodiesel yield. That sounds about right. Sodium hydroxide and potassium hydroxide used in base catalysts are readily available and cheap, but lipase catalyst produces more toxic wastewater. That's not right. The toxic wastewater from the base catalysis is the one that's the issue. Base catalysis involves only one step, while lipase catalysis involves many steps in the synthesis sequence, which turns to add to the cost of the process. I don't think that's right. The lipase catalysis does not involve many steps. I don't think so. And the base catalysis typically has a lower rate yield. No, that's not right. But lipase catalysis is sensitive to alcohol such as methanols, high energy cost. That's not true. Okay, so just put that one there. Right. One method of producing biodiesel is blah, 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 where triglycerides are converted into simple methyl esters of fatty acids. One of the following is a reactant. Which one of the following is a reactant of this transesterification reaction? Oh, I think you're missing a picture. Well, let's say, well, it's definitely not this because that's not made. It's definitely not this because, oh wait, it's a reactant. Oh yes, reactant. Read the question, Mr. Lim. Mr. Lim was looking at this as if this was products. Okay, so what's a reactant? It's not that, that's the product. It's not that, that's a product. It's this, because that is the reactant. And it's not that, because that's just weird. Right. Which one of the following substances completes the equation illustrating the process of transesterification to produce biodiesels, triglyceride plus a methanol? Right. Okay, next. Okay, what you got? Biodiesel, fuel, blah, blah, blah. There's that. Biodiesel can be synthesized using a base catalyzed reaction with methanol. The triglyceride breaks down into fatty acids, undergoes esterification, blah, blah, blah. State why the compounds above are described as an unsaturated oil. Okay, so this is all the way back to year 11. Unsaturated means that it has double bonds. Double bonds. Okay, so which one? So it has double bonds. I guess that's the answer. And where are those double bonds? There's one, there's one, there's one, there's one. All right. Draw the structural formula of the methyl ester formed by the section of molecule circled in the above diagram. This is... So what you do is you take your scissors out, you cut out this portion of the thing. Now you have it here and you drag it over there. You get your glue stick out and you glue it on. And then you draw in the methyl group on the end, and that is exactly going to do you very well. Don't worry about the other side of the exam. Who worries? Who needs to care about that? All right. Name a catalyst that can be used in this process. So again, this is going to be sodium hydroxide or lipase. Okay, as well as the methyl ester, the biodiesel, there's one other product. What is it? It's the glycerol. Please read the question because it says name... Oh, and draw. See, if Mr. Lim had not read that, you'd just be like, oh, it's glycerol. Boom, finished. Name and draw. Oh, glycerol. I'll draw it over here. 1, 2, 3. So make sure you read the questions all the way to the end. Okay, ethanol is bad for you. Don't drink ethanol. Okay. 2 main processes, blah, blah, blah. Which of the following statements is not correct regarding the hydrolysis of ethene to produce ethanol? Okay, increased pressure increases forward rate of reaction. That is a true statement. Okay, because you've got 2 particles on that side and 1 particle on that side. So therefore, an increased pressure will increase, it will actually increase forward rate of reaction. That makes sense because it's increased pressure. We should just be looking at the rate. It's also going to affect yield, increase the yield. That's true. Increased temperature increases the forward rate of reaction. That's going to be true because it's talking about rate, not yield. Okay, it's going to increased temperature will decrease the yield, but that's not what the question is asking. And the catalyst increases the yield. That's a false statement because catalysts don't affect yield. So it's D. All right, which of the following statements is not correct regarding the fermentation method of ethanol production? Performed at a lower temperature. That is a true statement. Performed at a lower pressure. That is a true statement. Less sustainable. That's a false statement. It is much more sustainable. The zymase enzyme provides an alternative reaction pathway with a lower activation energy. That's true for enzymes. Therefore, it's that one there. Next. Ethyl ethanoate. Oh, I didn't have much on ethanol, eh? All right. Ethyl ethanoate. So you get ethene turned into ethanol, turned into ethanoic acid. Then you add a little bit of ethanol to ethanoic acid and you make ethyl ethanoate. What are the processes here? So this is hydration. This here is oxidation. And this here is esterification. Which means that even from the first one is just A. All right. Which catalyst needs to be added to A, B, and C for reaction to take place as indicated? What catalyst? I think it is the acid. I don't know. Yeah, I think we use the H2SO4 for esterification. We use H2SO4 for oxidation, so probably use H2SO4 for the hydration as well. So we'll go with that. All right. See, so here is another one. So you do need an acid of some sort, so phosphoric acid can also be used there. All right. Following reaction sequence, blah, blah, blah. Phosphoric acid and sulfuric acid can act as catalysts in the reaction sequence. Explain using collision theory how a catalyst speeds up a chemical reaction. 2 marks. Okay, so lowers activation energy by providing alternate reaction pathway with lower EA, therefore a greater proportion of particles have sufficient energy to react, increasing frequency of successful collisions. All of that needs to be written to get those marks. Okay. Consider step 1 and step 2 for this reaction there, blah, blah, blah. What the hell step 2? Don't matter. Right. Write the equation for step 1 and explain why it's described as an addition reaction. Okay, fine. Addition reaction is because you're adding stuff to it. So ethene, I guess I'll write this as a structural formula, CH2 gas plus H2O gas goes to CH3CH2OH. Why is it an addition reaction? Because a double bond broken and I guess atoms added across double bond. Why not? Okay. Why is it described as a condensation reaction? So write the equation for step 2. So CH3COOH, ethanoic acid, can be liquid, can be aqueous, right? Plus your ethanol goes to ethyl ethanoate. So in this one here, you should get used to writing the carboxylic acid group first, so that you can get a nice COO there, and then you get this alcohol backwards there, right? Condensation reaction because you're going to produce some water. So I've defined it as condensation combines two small molecules into one bigger one, and produces water in the process. Okay, next. In step 1, 450 kg of ethene was reacted with excess steam and 48.5 kilograms of ethanol was produced. Calculate the percentage yield of this reaction. So this is a forward yield reaction. Okay, fine. So, first of all, you would work out the number of moles of ethene, which would be equal to 458,000 over whatever the molar mass of ethene is. That will get you some value. That value, then you could work out the number of moles of ethanol that you're theoretically supposed to be producing, which I think it is a 1-to-1 ratio with CH2. So that'll be equal to A. Then you would be able to say that the mass of CH3CH2OH theoretical produced would be the number of moles of ethanol times the molar mass of ethanol, which would be some value, something, and then you would take that percentage yield of the ethanol would be equal to B over 48500. All right, so then you would times that by 100 to get the yield, and so that would be some value there. All right, so the next one is the conversion of glucose to ethanol. So glucose is given to you there, so C6H12O6. Okay, and it's also been told that you make ethanol, which I'm just going to write its molecular formula here. Right, and carbon dioxide. Okay, so you have to try and balance this one out. So we'll balance out, let's try to balance out the hydrogens first. So we're going to have a 2 ratio there. So because there's a 2-to-1 ratio there, those two have to be in a 2-to-1 ratio because That's the only place that hydrogen can go, right? If there's two carbons, if there's 4 carbons here out of the 6, that means I should probably put a 2 here, and therefore that will make that 6 carbons, and then that will make 6 oxygens as well. Ta-da, done. All right. In this process, the reaction is catalyzed by enzymes. Describe 2 characteristics of enzymes that make them different from catalysts, such as phosphoric acids and sulfuric acids. Okay, so number 1, it's biological, and they're made out of proteins. Okay, and then maybe you could even use they only work under specific temperature and pH conditions. Those are 2 characteristics which makes them different. Okay, cool. Next. All right, last one, calculation. Woo. Okay, so biodiesel, blah, 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 blah. The vegetable oil in this reaction has a molar mass of that. If 1.5 tons of vegetable oil is reacted, what mass of ethanol will be required to react without this amount of oil? Okay, so let's do A. 1.5 tons of vegetable oil, 1500000, that's 1.5 tons, over 855.334 gets you the number of moles of oil, okay, which will be equal to some value here. Okay, what is the number of moles of methanol that you'll need? So the number of moles of methanol will be equal to number of moles of oil times 3 on 1, because it's a 3 to 1 ratio. So therefore it's A times 3, which will be equal to, whoops, does not make sense, which will be equal to some value B. Right, there's that one there. Okay, oh, wait, you need the mass. Read the question, Mr. Lim. And then the mass of methanol that is required will be B times whatever the molar mass of methanol is, which will be equal to some value. All right. Okay, so 3 different methyl esters, donated A, B, and C, are produced from this reaction. What is the mass of ester A produced in this process if the reaction is 78% efficient in the production of this ester? Okay, so B, then what we need to do is we say that, okay, I got the number of moles of oil, so I'm going to work out the number of moles of what's this, biodiesel A is equal to the number of moles of oil times 1 on 1. Let's have a think, because there's going to be a 1 here to 1 ratio there, okay, because you're splitting that big vegetable oil into thirds and one part of it goes there. All right, so that'll be equal to A, right? So this is the number of moles of biodiesel A that can be theoretically produced. All right, so you can work out the mass of biodiesel A that can be theoretically produced, which will be equal to A times the molar mass of that biodiesel A, which means that you would have to look at biodiesel A and work out how many carbons, hydrogens, and oxygens there are to work out its molar mass, and that would be some value called B. Then we would take the mass of biodiesel A actual would be equal to the mass of biodiesel A theoretical times, what's this, 78 over 100 to get the yield, which will be equal to some value B times 78 over 100, which will be equal to some value. Okay. Esters can also be produced by the reaction of a carboxylic acid with an alcohol. That makes sense. Draw the structure of the carboxylic acid that would be needed to produce ester A in the reaction above. Show hydrogen atoms. Ugh. So this is what you do. You take your because it says draw the structure, you can't do this, but you know, you can do this. I'm going to do this because Mr. Lim is lazy. And you would take that. Oops, that's not what I wanted. Crud. Take that, and then might make it a bit bigger, and then add a hydrogen on the end because that's the carboxylic acid there. All right. That's what you do. So remember, bring scissors and glue stick to your exams. All right, and use your understanding of the collision theory to explain the role of sodium hydroxide in this reaction. So again, what is the use of a catalyst? Okay, so that's E. What's that one? C. What's this one? B. Yeah, so cool. All right, so E, understanding collision theory. So catalyst reduces energy required for a successful collision by providing an alternative reaction pathway with lower activation energy. Right, therefore there's an increase in the proportion of particles that have sufficient energy, and so therefore there's an increase in the frequency of successful collisions. And that's Asher, stop drawing on it. Stop.